Okay, so now we're going to take a look at example 2, where we're asked to calculate the volume lying inside a sphere described by this equation here, and also inside the cone described by this equation here. Basically, the solid object that we're looking at looks kind of like an ice cream cone, right? So on the bottom is being described by this sphere, the cone, and the top is a portion of a sphere, so not the entire sphere. And then we're looking at the region inside the two objects. Okay, so first let's try to understand this sphere here. So we can rewrite this equation as x squared plus y squared plus z squared minus 2z is equal to 0. And if we complete the square, we get z minus 1 squared, but then I get an extra plus 1. So to balance the equation, I need to add 1 here. Okay, so this is a sphere. So this sphere is actually not centered at the origin, but at the z coordinate 1. So technically, this is not that important in setting up the integral, but it gives us an indication of understanding how this solid region is being described. Okay, so we want to be able to describe things in spherical coordinates, right? So let's first take a look at the sphere. So we want to convert to spherical coordinates, right? So for the sphere, we have this equation here, and so we want to use the change of coordinates to describe it, right? So we have x squared plus y squared plus z squared. So in polar coordinates, that's equal to rho squared. And on the right hand side, I have 2z. The z coordinate is rho cosine phi. So I make the substitution, rho cosine phi. Right, so I'm just plugging it into this equation here. And okay, so so I have this as the sphere, and then so let's simplify this, right? So I can cancel out one of the rows. Right, so one of the rows cancels out. And okay, so I get as the sphere, rho is equal to cosine phi. Okay, so that's for the sphere. So now let's do the cone. Right, so the cone is z squared is equal to x squared plus y squared. So let's do this substitution here, right? So rho is z equals rho cosine phi. So that's squared, and then x squared plus y squared. So we have rho sine phi cosine theta squared plus rho sine phi sine theta squared. Okay, so now let's simplify this. Right, so I have rho squared cosine squared phi is equal to rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Okay, so first of all, I can divide everything by rho squared, right? So that will cancel this, that will cancel this, that will cancel this. Okay, so now what else? So here, let's just leave this cosine squared phi. And on here, we have a cosine squared plus a sine squared. And so I can factor out this sine squared phi. And then the Pythagorean identity, this is just equal to 1. So I get cosine squared phi is equal to sine squared phi. Okay, so this is the same as saying, so I divide by cosine squared, right? So you get tangent squared is equal to 1. and taking the square root, you get tangent phi is equal to plus or minus 1. But here, and so let's think about this for a second, right? So here, phi is measuring from the North Pole, right? So starting from here, so this would be phi equals 0, and then we need to rotate in this direction up to this point here, and so this is where the cone is, and so here this is less than, we don't reach the xy plane, right? So phi doesn't get to pi over 2, so here we can ignore the minus 1 and just solve tangent phi equals plus 1, and so this tells me that phi has to be pi over 4. So that this describes the cone, right? So at this point here is where phi is equal to pi over 4. Okay, so this is going to describe the angle phi. Okay, so we now have ready to write down the whole description in spherical coordinates. Right, so first theta. So going back to the object, right? So the ice cream cone goes completely around this way. So that's a full rotation, 0 to 2 pi. And then for phi, we just discussed that, but basically phi equals 0 starts from the North Pole, and then it rotates only up to this portion of the sphere where it meets the cone, and the cone we've already determined was when phi equals pi over 4, right? So phi ranges between 0 and pi over 4, and then finally the parameter rho basically is starting from the origin and reaches to the sphere, right? And the sphere was described as cosine phi. So this goes up to cosine phi. So that this is, again, the cosine phi is describing the sphere. Okay, so so this is the description in spherical coordinates, right? So now we're ready to calculate. So the volume, again, to calculate a volume in triple integrals, that's just the triple integral over the region of the function 1 dv. And as usual, dv for spherical coordinates is rho squared sine phi d rho d phi d theta. Okay, so let's write down the triple integral. So theta goes between 0 and 2 pi. Phi goes between 0 and pi over 4. And then rho goes between 0 and cosine phi. We're integrating the function 1. But then dv is this thing. So I have to include that. So rho squared sine phi d rho d phi d theta. Okay, so this is the integral, the triple integral we have to calculate. So first, integrating with respect to rho, right? So we have the rho squared. So the antiderivative would be rho cubed over 3. The sine phi stays the same, and this is evaluated from 0 to cosine phi. The d phi still there, d theta still there. Okay, so now what do we have? So I have to plug in cosine phi. When you plug in 0, it's just 0. So this is what we get. So cosine phi cubed. So we have 1/3 cosine cubed phi sine phi d phi d theta. Okay, so now oh, whoops, I've made a mistake here. So looking back at my notes, okay, so going back into my notes here, this equation here was x squared plus y squared plus z squared is equal to 2z, right? So when I substitute in z here, there should be a 2. So there should be a 2 here, right? And so this should be 2 cosine phi. So this should be a 2 cosine phi here. Okay, so that throws things a little bit off, right? So there should have been a 2 cosine phi here, and there should be a 2 cosine phi here. Okay, so then when you substitute it in, 2 cubes is 8. So I have an extra 8 here. Okay, so that should fix things. Okay, so now we have to integrate this. So here, this can be done with a u substitution, right? So I'll let u is equal to cosine phi, so that du is minus sine phi d phi. So bring the minus sign over here, you got minus du is equal to sine phi d phi. Okay, so then basically this becomes 8/3. So u is cosine phi, right? So this is u cubed. And then the sine phi d phi becomes minus du, so you get a minus du here, right? So u substitution turns this into a power. So the antiderivative now would be, so that the negative 8/3 stays the same, and the antiderivative would be raising to the 4th over 4. And okay, so let's just save some time and just do the u substitution all at once, right? So I plug the u back in, so cosine phi, and then this needs to be evaluated from 0 to pi over 4. Okay, so that's what we have. So let's calculate this. So so I plug in the numbers, right? So let's see. The negative 8/3 divided by 4 gives me negative 2/3. So I get negative 2/3. And then, so that takes care of the coefficient. Okay, so then I have to plug in the numbers, right? So pi over 4. So I have cosine pi over 4 to the 4th power minus, and I plug in 0. So that's cosine of 0, which is just 1. Also raised to the 4th power. D theta. Okay, so now this becomes the integral from 0 to 2 pi. Cosine of pi over 4 is 1 over the square root of 2. But when I still have to raise it to the 4th power. And then, as I said, cosine of 0 is 1. 1 to the 4th is 1, so that's minus 1. D theta. Okay, so so what do we have? So I can pull out the minus 2/3. That's just a coefficient. Integral from 0 to 2 pi. This raised to the 4th is so you get 1/2, and that's squared again, so you get 1/4. So this is 1/4 minus 1. 1/4 minus 1 is just minus 3/4. So you get minus 2/3 integral from 0 to 2 pi minus 3/4 d theta. Then I can just multiply these two numbers, right? So that's 1/2 integral from 0 to 2 pi d theta. This is just the length of the interval, which is 2 pi. So it's 1/2 times 2 pi, which is equal to pi. Okay, so so we've calculated that the volume of this object is equal to pi. Okay, so initially I made this little mistake here. I forgot about the 2 here, but we fixed that, and so this calculation should be correct now.